a quiet archive record. Tonight, we pass into a world that asks nothing of you. No urgency, no weight, just the quiet unfolding of a story. Artemis II is NASA's first crewed mission of the Artemis program, built to send astronauts around the moon and bring them back safely. It is not a landing mission. It is a full end-to-end test of the people, the spacecraft, the rocket, the ground systems, and the decision-making that will be needed later for missions that do land. Artemis II centers on a single vehicle stack: the Space Launch System rocket, the Orion spacecraft, and the systems that support them. The mission is also a checkpoint for larger goals, from deep space navigation to radiation protection, to long-duration operations far from Earth. It ties together a long chain of history, engineering, politics, suppliers, tests, and hard lessons learned. Tonight, we go through everything on the NASA Artemis II mission. Start with what Artemis II is, in plain terms. It is a crewed flight test that launches on the Space Launch System, carries a crew inside Orion, performs a translunar injection burn to leave Earth orbit, travels toward the moon, swings around it on a distant retrograde-like path, called a lunar flyby trajectory, and returns to Earth for a high-energy reentry and ocean splashdown. That short description hides the fact that nearly every part of the mission is either new, revived after decades, or rebuilt to meet modern safety and certification rules. In NASA planning, Artemis I was the uncrewed flight test. Artemis II is the first time people ride Orion and SLS together. Artemis III is the first attempt to land people near the moon's south pole using a separate human landing system. Artemis II matters because it is the mission that turns a set of test articles, demos, and paperwork into an operational crewed system. If Artemis II is not solid, then Artemis III becomes much harder to justify. The Artemis II crew is 4 astronauts. The mission uses a European-built service module which provides propulsion, power, air, water management, and thermal control. The crew rides in the American-built crew module, the conical capsule that is the only part that returns to Earth. The 2 modules together form Orion. Orion sits under a launch abort system on top of the SLS rocket. The stack is tall, heavy, and packed with systems that must survive vibration, acoustic loads, temperature swings, vacuum, and radiation. To understand Artemis II, it helps to break it into phases, because each phase has different risks. Phase 1 is the countdown and launch, where the rocket and ground systems must behave perfectly in a short window. Phase 2 is ascent to orbit, including stage separation and engine performance. Phase 3 is Earth orbit operations, where Orion is checked out and prepared for the burn that sends it toward the moon. Phase 4 is the translunar coast and lunar flyby. Phase 5 is the return coast. Phase 6 is entry, descent, and recovery. The launch vehicle is the Space Launch System, or SLS. SLS is a heavy-lift rocket that uses heritage space shuttle-era hardware, but in a new configuration. It has a large core stage, powered by 4 RS-25 engines. Those engines are modernized versions of the Space Shuttle main engine. On the sides of the core are 2 solid rocket boosters. These boosters are derived from shuttle boosters, extended with an extra segment for more thrust and duration. Above the core stage is an upper stage. For early SLS flights, that upper stage is the interim cryogenic propulsion stage, or ICPS, based on the Delta IV upper stage. It carries liquid hydrogen and liquid oxygen and uses a single RL-10 engine. SLS is designed to throw a large mass toward the moon in one launch. That is its central promise. It avoids complex assembly in low Earth orbit for the core crew vehicle. It also concentrates schedule, budget, and risk into one giant rocket. SLS has been criticized for cost. It has also been defended as the only near-term vehicle NASA had funding and political support to build at that scale. Artemis II is an important moment because it is the first time the system must meet crew safety expectations. Crew safety begins with the launch abort system. Orion sits under a tower with 3 motors. The abort motor can pull the crew capsule away from a failing rocket in milliseconds. The attitude control motor can steer the capsule during an abort. The jettison motor can throw the tower away when it is no longer needed. The abort system is used only in emergencies, but it must work on the first try, every time. It is tested through motor firings and an ascent abort test flight, but a real abort is unpredictable. That is why there are strict rules about margins and fault tolerance. Orion itself is built around the idea of deep space reentry. Returning from the moon means hitting Earth atmosphere at roughly 11 kilometers per second. That is far faster than a typical low Earth orbit return. The heat shield must handle higher energy. The capsule must keep the crew alive during the coast, and then survive a hard thermal and mechanical environment at entry. Orion uses an ablative heat shield made from a material called avcoat. It was developed for Apollo and redesigned for Orion. The shield is thick, heavy, and carefully inspected. The crew module is relatively small compared to the International Space Station, and even compared to many modern spacecraft concepts. 4 people in a tight capsule for days is not comfortable. NASA's focus is not comfort. It is survivability, redundancy, and a clear path to certification. The inside includes seats, displays, controls, storage, life support equipment, and waste management. There are also provisions for food, water, and sleep. One part of Artemis II is learning what the crew can realistically do in that environment. The European Service Module is one of the most important pieces of international cooperation in the mission. It provides the main engine used for major burns after the upper stage separates. It also provides solar arrays, batteries, oxygen and water storage, thermal radiators, and propellant tanks. Its design has heritage from ESA's automated transfer vehicle, which visited the International Space Station. But Orion's service module is adapted for deep space operations and for Orion's specific needs. The mission trajectory is designed to be safe and to provide key tests. Artemis II is expected to perform a lunar flyby. It does not enter lunar orbit for a long stay. It passes by the moon, reaches a maximum distance from Earth that can exceed the Apollo missions, and returns. The exact profile can vary. What matters is that Orion travels through deep space, navigates far from Earth, and returns with the right timing and energy. Navigation is not simply pointing at the moon. It involves a chain of sensors and ground tracking. Orion uses star trackers, inertial measurement units, and optical navigation methods. It also uses communications with the deep space network. The crew can take manual control if needed, but most of the flight is guided by onboard software and ground monitoring. A test like Artemis II proves not only that the software works, but that the team can operate it, interpret it, and respond to anomalies. Communications in deep space are different from low Earth orbit. The signal is weaker. The time delay is longer. Coverage depends on the deep space network antennas and their schedules. Orion uses multiple antennas and frequencies. It also uses systems to relay voice, telemetry, and video. Artemis II is a chance to confirm that the end-to-end communications and tracking network supports a crewed mission profile. There is also the question of radiation. Leaving low Earth orbit means leaving much of Earth's magnetic protection. The crew will be exposed to higher levels of cosmic radiation. The mission is short compared to a Mars flight, but it still matters. Orion includes radiation protection features and monitoring devices. NASA uses forecasts and space weather monitoring to reduce risk from solar particle events. Artemis II operations will include the procedures for how to respond if the sun produces a sudden burst of energetic particles. For many people, the main story of Artemis II is the crew and the flight. But the deeper story is a long sequence of tests and failures that come before launch. SLS and Orion have both faced delays. Orion's first crew module for Artemis I had issues with valves in the service module. Artemis I itself was delayed by multiple scrubbed launches, hydrogen leaks, sensor problems, and weather. Those experiences feed directly into Artemis II planning. Ground systems at Kennedy Space Center are a major part of Artemis II. The vehicle assembly building, the mobile launcher, the crawler transporter, the launch pad, the fueling systems, the software that controls the count, and the teams that run it all must work together. A modern launch campaign is more than a rocket. It is a factory-like operation that must be precise and repeatable. The mobile launcher is a tall steel structure that carries the rocket from the assembly building to the pad and provides platforms, connections, and umbilicals. The crawler transporter moves it slowly along a crawlerway. The launch pad provides the flame trench, sound suppression water system, and many hookups. Hydrogen and oxygen are loaded as super-cold liquids. Hydrogen in particular is difficult because it is so cold and because its molecules are small enough to leak through tiny imperfections. Countdown procedures are built around constraints called launch commit criteria. These criteria define what must be true to proceed. They include weather rules, hardware status, range safety rules, and sensor readings. If the criteria are not met, the count stops. Artemis II will follow strict commit criteria, with additional rules for crew safety. On launch day, the crew must board Orion, strap in, and complete checks. There are escape routes and emergency procedures. The team monitors environmental control to ensure the crew has air and the right pressure. The rocket is fueled. The solid rocket boosters are armed. Then, at the right time, the RS-25 engines ignite and ramp to thrust, and the boosters light. The first minutes of flight are violent. The rocket shakes. The loads are high. The acoustic pressure is extreme. This is why the sound suppression system dumps huge amounts of water at launch. The boosters provide most of the thrust at liftoff. After roughly 2 minutes, the boosters separate. They fall into the ocean. The core stage continues to burn for several more minutes. Stage separation is a crucial event. When the core stage shuts down, the upper stage ignites. The upper stage then pushes Orion into a stable orbit. After shutdown, Orion separates. The launch abort system tower is already jettisoned earlier once it is no longer needed. Orion then performs a sequence of checkouts. In Earth orbit, Orion must verify its power systems, communications, guidance, navigation, control, life support, and propulsion. The crew checks displays and controls. The ground checks telemetry. They make sure that nothing was damaged and that nothing is behaving oddly. Then they prepare for the translunar injection burn. Translunar injection is the burn that leaves Earth orbit. In Artemis II, that burn is expected to be performed by the upper stage, not by Orion. The upper stage uses its RL-10 engine to add speed at the right point in orbit. The timing matters because it sets the path to the moon and the return geometry. After the burn, Orion separates from the upper stage and proceeds on its own. Once Orion is on a translunar trajectory, it is a spacecraft in deep space. The crew can perform checks and small maneuvers. Orion can test its attitude control system, which uses small thrusters to maintain orientation. It can test communication and navigation. The mission can include demonstration tasks, such as taking images, testing manual control, and practicing procedures. Artemis II also includes planned demonstrations of life support and crew operations. Orion's environmental control and life support system must manage carbon dioxide removal, humidity control, temperature, and cabin pressure. It must provide enough oxygen and remove contaminants. It must handle waste. These systems are complex and must function for the entire mission. One critical part is water management. The crew needs water for drinking and for food. The system must prevent contamination and keep supplies within limits. Another part is thermal control. In space, heat does not leave through air. It must be radiated. Electronics and people produce heat. The service module radiators and thermal loops move heat to radiators. Power comes from solar arrays on the service module. They must deploy correctly. They must point correctly. The spacecraft must manage power distribution and battery charging. The arrays are large and are one of the most visible parts of Orion. Their performance matters for communications, computing, and life support. As Orion approaches the moon, it will perform a flyby. The moon's gravity will bend the trajectory. The exact distance from the lunar surface depends on the mission design. The flyby allows tests of navigation and trajectory correction maneuvers. It also gives the crew a view that is both historic and practical. It confirms the vehicle is where it should be. After the flyby, Orion heads back to Earth. The return trajectory is chosen so that if certain systems fail, the spacecraft can still return safely. NASA often prefers trajectories that are called free return, meaning that the path around the moon naturally returns toward Earth without major burns. Orion can still perform burns for targeting and adjustments, but the baseline aims to protect the crew from being stranded. The final and most dangerous phase is reentry. Orion approaches Earth at high speed. It must enter the atmosphere at the right angle. Too steep, and it can overheat or experience extreme deceleration. Too shallow, and it can skip back out into space. The guidance system controls the capsule's orientation to manage lift and heating. Orion uses parachutes to slow down after atmospheric entry. There is a sequence: drogue parachutes, then main parachutes. The parachutes must deploy correctly, inflate correctly, and carry the capsule to a safe splashdown speed. Parachute systems have many failure modes, and NASA tests them extensively. After splashdown, recovery teams move in. They secure the capsule, ensure the crew is safe, and bring them onto a recovery ship. This is another key part of Artemis II. It is not enough to survive re-entry. The crew must be recovered quickly, safely, and in a controlled way. That is the high-level mission. Now go deeper because the details are where Artemis III becomes a story about industrial capability and long-term continuity. Artemis II exists because NASA and its partners decided to return to the Moon with a new architecture. After the Space Shuttle retired, NASA focused on the International Space Station and commercial crew for low Earth orbit. Deep space required a different set of systems. There was also a policy drive to maintain heavy lift capability in the United States. SLS and Orion emerged from that environment. Orion began as the crew exploration vehicle under the Constellation program. Constellation was cancelled, but Orion survived. It was reshaped, renamed, and repurposed. SLS came later, built around Shuttle and Apollo heritage, with a new core stage and an upper stage. The program faced budget constraints and shifting schedules. The result is that Artemis II is flying hardware that has been in development for a long time. That is both a strength and a risk. It is a strength because many components have been studied and tested for years. It is a risk because requirements change, suppliers change, and the workforce must carry knowledge across decades. SLS core stage is built by Boeing at the Michoud Assembly Facility in Louisiana. It is a giant tank structure with liquid oxygen on top, liquid hydrogen below, and an engine section at the bottom. The RS-25 engines are mounted there. Each engine is complex, with turbopumps and controllers. They were designed for reuse on the shuttle, but on SLS they are expended. They have been upgraded with new controllers for modern avionics. The solid rocket boosters are built by Northrop Grumman. They are large segments of solid propellant stacked together. The boosters produce tremendous thrust. They also produce a lot of vibration and acoustic energy. Their exhaust contains aluminum oxide particles that create a bright plume. The boosters have to separate cleanly and reliably. The upper stage for Artemis is the ICPS. Later, SLS missions are planned to use a larger exploration upper stage. ICPS is smaller, but it can still perform the translunar injection burn for Orion. It uses an RL-10 engine, a well-known engine family with long history. But again, a long history does not mean a simple integration. Orion's crew module is built by Lockheed Martin. The pressure vessel, heat shield, windows, and internal systems must all be integrated. The crew module must be strong, but not too heavy. Every kilogram matters. The capsule must be sealed. It must withstand landing loads. It must provide adequate visibility and control access. The service module is built by Airbus for ESA. Its main engine is derived from the Space Shuttle's orbital maneuvering system engine, refurbished and adapted. It also has a set of auxiliary engines and small thrusters. Its solar arrays are distinctive, arranged in an X shape. They are built to provide enough power in deep space. One area where Artemis II differs from Artemis I is the life support system. Artemis, I did not carry people, so it did not fully exercise crewed life support. Artemis II must. That means more sensors, more operational constraints, and more failure cases. It also means that the crew can report how the capsule feels, which is a kind of data you cannot get from uncrewed sensors alone. The mission also includes a new spacesuit and crew survival system for launch and entry. NASA uses suits for pressure and protection. The suits must integrate with seats, harnesses, and emergency systems. They must be comfortable enough to wear for long periods. They must not interfere with movement or controls. Another difference is the training and procedures. A crewed mission is not just hardware. It is a trained team both in the capsule and on the ground. NASA has flight controllers, engineers, managers, safety officers, range safety, recovery teams, and many contractors. They run simulations. They run rehearsals. They practice anomalies. NASA uses a method called integrated simulation, where the crew and the mission control team practice together. They can inject failures. They can test decision-making. They can learn how communication patterns work. Artemis II requires many of these sims to be completed before flight readiness. There are formal reviews that gate the mission. There is a design certification review for the vehicle. There are flight readiness reviews. There are safety and mission assurance checks. There are readiness polls. These are not just meetings. They are where problems are forced into the open. It is where managers decide what risks are acceptable. One key concept is risk acceptance. Spaceflight is never zero risk. NASA uses a structured approach to estimate the probability of loss of crew and loss of mission. They use fault tree analysis. They use probabilistic risk assessment. For Artemis II, NASA must decide that the risk is within a range they consider acceptable for a test flight. A major risk driver is the rocket itself. SLS is new in its integrated form, even though it uses heritage parts. Artemis I provided data, but Artemis II adds crew and changes in configuration and procedures. It also adds the pressure of having people on board. That changes the posture of every team. Another risk driver is Orion's heat shield and reentry system. Returning from the moon is a severe environment. Artemis. I tested Orion at lunar return speeds, and it performed well. But Artemis II must replicate that with a different crew module, with crewed systems and potentially different mass and center of gravity. The parachute system is also critical. Orion uses a cluster of main parachutes. There are multiple chutes for redundancy, but the system must deploy in the right sequence. NASA tests these systems with drop tests, including using aircraft and test articles. Still, flight is different from test. Artemis II will provide the most important real-world validation. Then there is the human element. The crew must manage fatigue, workload, and situational awareness. The capsule is small and noisy. The schedule must allow rest. The mission timeline must include quiet periods, sleep periods, and time for meals. The crew must also conduct checks and demonstrations. Artemis II is also a public mission. NASA will share images and video. The crew will likely speak to the public during the flight. But the mission's core job is engineering validation. The communications plan must not interfere with safety or operations. Now, look at what the mission is expected to demonstrate for later missions. Artemis III and beyond require that Orion can rendezvous and dock with other vehicles, such as a lunar lander or the Gateway Station. Artemis II is not expected to dock with Gateway, but it will still validate many of the systems needed for docking operations, such as navigation, guidance, and communications. Orion's docking system uses a standardized interface called the NASA Docking System. It is similar in concept to the International Docking System standard used by commercial crew vehicles. Docking requires precise control. It requires sensors and software that can guide to millimeter-level alignment. Artemis II may test parts of this, even if it does not perform a dock. Another key test is deep space operations with the crew. On the space station, there is constant ground coverage, frequent resupply, and many escape options. On Artemis II, the crew is farther, the rescue options are limited, and the systems must be more autonomous. This is a step toward the kind of operational independence needed for future missions. There is also the test of recovery operations. Apollo had recovery at sea. Modern NASA still uses sea recovery for Orion. That means ships, helicopters, divers, and specialized equipment. The capsule must be safe to approach. There can be residual propellants or pressurized systems. The crew may be disoriented. The recovery plan must handle these realities. The mission is also part of a larger industrial story. Artemis II uses a supply chain spread across the United States and Europe. It uses contractors, subcontractors, and government facilities. It uses materials like composites, aluminum lithium alloys, insulation foams, seals, wiring harnesses, and countless fasteners. Each has to be tracked and certified. For crewed spaceflight, quality assurance is strict. Parts have serial numbers. Processes are documented. Non-conformances are tracked. If a part is out of spec, it can trigger investigations. This culture of documentation can feel slow, but it exists because small mistakes can cause catastrophic failure. SLS and Orion are also shaped by politics. Funding is allocated by Congress. Jobs are distributed across states. Contracts are awarded with political considerations. This is not unique to Artemis, but it is prominent. It affects schedules and designs. It also makes the program harder to change quickly. The Artemis II schedule has moved over time. Dates have shifted due to hardware readiness, test results, and budget. NASA has to balance the desire to fly soon with the need to complete required work. For a crewed test, rushing is dangerous. Delaying is expensive and can erode support. The mission exists within that tension. Now focus on the spacecraft systems that the crew will interact with. Orion uses a modern cockpit with digital displays. The crew can monitor system status, view timelines, and control functions. The software is complex. It must be robust against faults. It must not crash. It must handle sensor errors gracefully. Guidance, navigation, and control is the system that keeps Orion pointed and stable. It uses reaction control thrusters and potentially auxiliary engines for larger maneuvers. It uses sensors like star trackers. It uses inertial measurement units. It uses algorithms that integrate data and estimate the spacecraft state. The propulsion system includes the main engine on the service module and smaller thrusters. Propellant management is critical. Tanks must remain pressurized. Valves must open and close correctly. The system must avoid leaks. Deep space is unforgiving. A leak can mean loss of control or inability to correct trajectory. Thermal control uses radiators and fluid loops. The system must keep electronics within temperature limits. It must also keep the cabin comfortable enough. Temperature extremes in space can vary, depending on whether the vehicle is in sunlight or shadow. The vehicle attitude can be used to manage heating, but attitude is also constrained by communications and power generation. The environmental control system handles carbon dioxide removal. Humans exhale carbon dioxide. If it builds up, it becomes dangerous. The system uses filters and scrubbers. It also manages humidity. In a sealed cabin, moisture from breathing and sweat can condense. The system must prevent mold and protect electronics. There are also fire safety and contaminant monitoring systems. A fire in a spacecraft is a severe emergency. NASA designs materials and procedures to reduce fire risk. They monitor oxygen levels. They keep fire extinguishers. They train the crew for fire response. Then there is the question of what Artemis II will do in terms of experiments or payloads. The mission is primarily a test, but it may carry small technology demos. It may carry radiation sensors. It may carry cameras and systems to record data. These payloads must not interfere with core mission systems. There is also a story about the moon itself. Artemis II's path around the moon is not just a scenic route. The moon's gravitational field is uneven. There are mass concentrations, called mascons, that can affect orbits. For a flyby, the effect is small, but navigation and tracking still must account for the moon's gravity field. The mission also passes through regions of space where Earth and moon gravity interplay. When Orion returns, it performs a sequence called entry interface, where it hits the top of the atmosphere at high speed. It then uses a guided entry to manage lift. Unlike Apollo, Orion has a more modern guidance system. It can adjust its flight path within limits. This helps control where it lands and how much heat it experiences. After the peak heating phase, the capsule slows. Then it deploys parachutes. There is also a set of airbags or other features to protect the crew. Orion splashes down. Then recovery begins. The success of Artemis II's will be measured by many metrics. Did the rocket perform within expected parameters? Did Orion's systems perform? Did life support maintain safe conditions? Did communications work? Did navigation and burns hit targets? Did re-entry produce the expected heating and loads? Did parachutes deploy correctly? Was splashdown within the planned zone? Was recovery quick and safe? NASA will also examine small anomalies. A sensor reading that is slightly off can lead to design changes. A valve that behaves oddly can lead to inspection across multiple vehicles. Artemis II will produce a large set of data. That data will inform Artemis III and later missions. Now step back and consider the broader Artemis program. Artemis includes more than SLS and Orion. It includes lunar landers, spacesuits for the surface, a lunar space station called Gateway, lunar communications networks, lunar terrain vehicles, and science payloads. Artemis II is focused on the transportation of crew around the moon, but it is part of that larger ecosystem. Gateway is planned to orbit the moon and serve as a staging point. Artemis II does not require Gateway, but the long-term plan often includes Orion docking to Gateway. Gateway itself is planned to be built by international partners and commercial providers. It adds complexity. Artemis II is a simpler mission in comparison, which is intentional for the first crewed flight. The human landing system is another major component. NASA selected SpaceX to provide the first lander for Artemis III, based on Starship. That lander is a separate vehicle that must rendezvous in lunar orbit. Orion does not land. It brings the crew to lunar orbit, then the lander carries them to the surface and back. This architecture makes Artemis II a test of the Orion part of that chain. Spacesuits for the surface are also a major challenge. NASA has moved toward commercial partners for suit development. Artemis II does not use surface suits, but it still uses launch and entry suits. It also uses procedures for emergency egress. Artemis II also touches on the question of what a successful lunar return means in the modern era. Apollo was a short, intense program. Artemis is planned as a longer, sustained effort. That means building infrastructure and repeating missions. To do that, the system must be reliable enough, and the program must be funded long enough. Costs are a major issue. SLS and Orion are expensive. Some argue that commercial heavy lift could replace SLS. Others argue that SLS provides unique capability and stability. Whatever the argument, Artemis II is a reality check. If it works well, it strengthens the case for continuing. If it has major failures, it can reshape the program. Now go into what can go wrong, because understanding Artemis II requires understanding its failure modes. A launch scrub can happen for many reasons. Weather, range issues, hydrogen leaks, sensor errors, valve problems, or ground system faults. Artemis, I had several scrubs. Artemis II will likely also face constraints. NASA will not launch if data is uncertain. During ascent, engine anomalies can happen. RS-25 engines are powerful and complex. Sensors can detect issues. If thresholds are crossed, the rocket can shut down engines early. The flight software can compensate to some extent, but there are limits. Solid boosters cannot be throttled or shut down once lit, which makes abort scenarios complicated in the first minutes. An abort is the scenario the launch abort system is built for. If a major failure happens, the abort motor can pull the capsule away. The crew then must survive an abort trajectory, deploy parachutes, and land in the ocean. NASA trains for this, but a real abort would be chaotic and dangerous. In orbit, system failures can happen. If a solar array does not deploy, power is reduced. If a thruster leaks, attitude control is compromised. If a communications system fails, the vehicle can still operate, but the ability to coordinate is reduced. NASA designs redundancy, but redundancy is not infinite. During trans-lunar coast, trajectory correction maneuvers may be needed. If Orion cannot perform burns, it can miss the target corridor and return path. A free return trajectory reduces risk, but it does not eliminate the need for accurate targeting. Near the moon, navigation errors can accumulate. The deep space network tracking helps. Optical navigation helps. But the system must also handle updates. Artemis II operations will test the process of planning and uploading burns, verifying them, and executing them. On return, reentry is the biggest physical stress. If the heat shield has defects, it can fail. If guidance is wrong, the capsule can enter at the wrong angle. If parachutes fail, landing speed can be fatal. These are the areas NASA focuses on in certification. Recovery can also be risky. The capsule can be unstable in water. Conditions can be rough. The crew can be injured. The recovery team must work fast. There are procedures to stabilize the capsule and open it safely. NASA deals with these risks through testing and process. They test engines. They test tanks. They test parachutes. They test software. They run simulations. They rehearse. Artemis II is the point where those tests become a real crewed flight. Now, to keep the story complete, trace the mission from the factory floor to the pad. SLS core stage is welded and assembled at Michoud. It is shipped by barge to Florida. There it is, integrated with the engine section and RS-25 engines. The boosters arrive as segments and are stacked in the vehicle assembly building. The core stage is stacked between the boosters. The upper stage is stacked above. Then Orion is stacked on top. Orion is assembled and tested separately. The crew module is integrated with the service module. The combined vehicle is tested for electrical and functional performance. It is fueled late in the process, depending on propellant type. The launch abort system is installed. The full stack is then rolled out. Rollout to the pad is slow. It is a visible event, but it is also a complex operation. Weather and wind can affect rollout. The crawler transports the mobile launcher and rocket. The stack then sits at the pad for final preparations. Wet dress rehearsals are a type of test where the rocket is fueled and the count is run without launching. Artemis. I had wet dress rehearsals with issues. Artemis II can use similar tests to validate systems. Each test can uncover problems. Software is another key part. Modern rockets and spacecraft are software-driven. SLS has flight computers. Orion has flight computers. Ground systems have control software. Errors in software can cause scrubs. NASA uses extensive verification, but integrated systems can still behave in unexpected ways. The mission timeline includes planned callouts and checklists. The crew has tasks. Mission control has tasks. There are defined points where they stop and evaluate. There are go or no-go polls. The goal is to reduce surprises. Now consider the crew themselves. Artemis II crew selection reflects NASA priorities. They choose experienced astronauts who can handle a test flight. They include a mix of backgrounds: test pilots, engineers, scientists. They also include international representation through partners on the program. In broader terms, but Artemis II crew is NASA and CSA, reflecting collaboration. Training includes Orion systems, SLS ascent profile, abort modes, deep space navigation procedures, reentry and landing, survival training, and recovery operations. The crew trains in simulators. They train in mock-ups. They train in water for splashdown recovery. They also train for medical emergencies. In deep space, you cannot evacuate quickly. The crew must handle medical issues with limited resources. They carry medical supplies. They train in basic procedures. Mission control includes flight surgeons. One of the biggest differences between a low Earth orbit mission and a lunar mission is the communication delay and dependence on the deep space network. Even a few seconds of delay changes how conversations work. It changes how time-critical operations are performed. Artemis II is a test of that human communication environment. Now, to make this a complete record, include the context of why this mission is called Artemis. Artemis in Greek mythology is the twin sister of Apollo. NASA chose the name as a direct link to the Apollo program. Apollo has sent humans to the moon in the 1960s and 1970s. Artemis is intended to return humans to the moon and establish a longer-term presence, with goals that include using lunar resources, doing science, and preparing for Mars. The Apollo program was built under Cold War urgency and large budgets. Artemis operates in a different era, with different politics and different partners. It is more distributed. It uses contractors and commercial providers more heavily. It also shares the space environment with many more actors, including other nations. Artemis I takes place in a world where China has its own lunar ambitions, where private companies build rockets at high rates, and where satellites and space debris crowd low Earth orbit. Even though Artemis II goes beyond low Earth orbit, it is part of that modern landscape. Now bring the narrative back to the mission itself, and go through the key hardware elements one by one, with enough detail to make the system feel real. Start with the RS-25 engines. Each engine burns liquid hydrogen and liquid oxygen at high pressure. It produces over 2 million newtons of thrust. It is a staged combustion engine with a complex flow path. It has many sensors. For the shuttle, the engines were reused. For SLS, they are used once, but they still must meet strict performance standards. The boosters are solid motors. They have a steel case. Inside is solid propellant cast into segments. Once lit, the propellant burns and produces high-pressure gas that exits through a nozzle. The nozzle can gimbal to steer. The boosters provide most of the initial thrust, and they are one of the defining visual features of SLS. The core stage tanks are huge. Liquid oxygen is stored at around minus 183 degrees Celsius. Liquid hydrogen is stored at around minus 253 degrees Celsius. The insulation must prevent boil-off and ice buildup. During fueling, the rocket vents. Hydrogen can leak. Managing that safely is a major part of the count. The upper stage uses the RL-10 engine. RL-10 burns liquid hydrogen and liquid oxygen as well. It is known for high efficiency. It can restart. It is used on many launch vehicles. For Artemis II, it must perform the trans-lunar injection burn reliably. Then Orion. The crew module has a pressure vessel, heat shield, and parachutes. It has avionics, displays, and life support. The service module has propellant tanks, solar arrays, and the main engine. It is the part that stays in space and burns up on return. Orion also has a system for separating the service module before re-entry. At the right time, the crew module separates. The crew module then orients for entry. This separation must be clean. It is a key event. The heat shield is the interface between deep space and the atmosphere. It is designed to ablate, meaning it slowly burns away and carries heat with it. The shape of the capsule produces lift. By rolling and changing its attitude, Orion can control its path. Parachutes deploy after the capsule slows. Drogues stabilize. Then mains deploy. The mains are large and provide the final deceleration. Orion then hits the ocean. The capsule can float in different orientations, and it has systems to right itself. Recovery teams then attach lines and bring it to the ship. The crew is extracted. Medical checks follow. Then the capsule is brought back for inspection. Inspection after flight is crucial. NASA will examine the heat shield, parachutes, and systems. They will compare predicted models to actual performance. They will use that to refine Artemis III. Now include the idea of certification. NASA does not just fly and hope. They certify the rocket and spacecraft for crew. That includes analyzing every critical system, verifying that failures are either unlikely or mitigated, and proving that the system meets requirements. Certification includes structural analysis. The rocket and spacecraft must handle loads. It includes vibration analysis. It includes thermal analysis. It includes software verification. It includes testing at component and system level. Artemis II is part of the certification story. A crewed flight test provides data that cannot be obtained any other way. It validates the integrated system in the real environment. Finally, consider what success looks like for the public. For many people, it is simple. A crew launches, goes around the moon, and returns. That is the iconic image. But within NASA, success is also a long list of technical objectives met and a set of unknowns reduced. Artemis II is therefore both a mission and a milestone. It is a moment where a long chain of plans becomes a real flight, and where the next missions become more plausible. To see why NASA treats this as a turning point, it helps to walk through the specific objectives that Artemis II is meant to close out. Not every objective is public in the form of a simple checklist, but the themes are clear. First is crewed integration. Artemis. I showed that SLS and Orion can fly, but Artemis II must show that they can fly with people inside. with life support running, with crew procedures in place, and with the extra constraints that come with protecting humans. It is not only a hardware test, it is a test of the entire system: training, rules, ground support, and decision-making. Second is end-to-end mission operations beyond low Earth orbit. Artemis II exercises the deep space network planning, communications handovers, tracking and navigation updates, and the tempo of deep space flight control. In low Earth orbit, there is often continuous contact through relay satellites and ground stations. In lunar space, coverage is a schedule. Artemis II proves that the team can live inside that schedule without losing situational awareness. Third is performance of critical events that are hard to fully certify on the ground: separation events, deployments, and thermal behavior in the real environment. This includes solar array deployment and pointing, thermal control during long coasts, propellant management under microgravity, and the behavior of electronics and sensors after launch vibration. Fourth is the return. Orion is designed around the idea that a lunar return is a different category of reentry. Artemis, I proved the basic heat shield concept in flight, but Artemis II proves it with the full crewed vehicle configuration and with full mission operations leading into entry. Now go deeper into the mission timeline itself, because a lunar mission is built around a sequence of planned calls, control modes, and flight rules. Before launch, NASA runs a formal launch readiness review. This is not a ceremony. It is a structured process where each subsystem and each organization states whether it is ready and under what constraints. A go is not blind optimism. A go is a statement that known issues are either resolved, mitigated, or accepted with documented risk. If an item is not ready, it becomes a constraint or a hold. Then comes the launch campaign at Kennedy. Hardware arrives, is inspected, and is integrated. Orion is processed in its own facilities, then mated to the launch vehicle stack in the vehicle assembly building. The entire stack is checked in place. Connections are verified. Umbilicals are tested. The pad infrastructure is checked. In parallel, the crew's schedule ramps up. The astronauts train, review procedures, and run simulations. They also rehearse launch day operations. NASA performs a dry dress rehearsal for the crew, which is a practice run of suit up, transport to the pad, boarding, and communications checks. This reveals friction points that are easy to miss when you are only looking at hardware. A major point of attention is the emergency response plan. During launch and entry, time is short. The crew and ground team need a clear plan for fire, depressurization, toxic exposure, a pad abort, and a water landing. Artemis II uses a modern set of rescue and recovery assets. But the basic problem is the same as it was for Apollo. You must move fast in an unforgiving environment. On launch day, the countdown begins with a long series of checks. Propellants are loaded. The rocket is conditioned thermally. The engines are prepared. Ground computers and vehicle computers are synchronized. The range is cleared. Weather is monitored. Hydrogen leaks are watched closely. A key lesson from Artemis I was that the fueling system and its seals can create unexpected delays. Cryogenic hydrogen can escape through tiny paths, and when it does, it can lead to red lines that force a stop. Artemis II planning includes changes in procedures and hardware to reduce that risk, but the basic physics has not changed. Handling super cold hydrogen at high flow rates is hard. When the crew is on board, the stakes change and the pace of decisions changes. Fueling can still be held, but human endurance and suit systems become factors. The crew has limits on how long they can sit strapped in. The cabin environment must remain safe. These constraints become part of the launch commit criteria. At liftoff, SLS produces intense sound and vibration. This is why NASA uses a water sound suppression system. The purpose is not just to reduce noise. It is to reduce acoustic energy that can damage vehicle structures and electronics. The stack must survive the first seconds without exceeding design loads. During ascent, the flight control system steers the vehicle. The guidance is designed to target orbit and to manage loads, including a region called max Q, where aerodynamic pressure is highest. The rocket also performs a roll program, rotating to a planned orientation so that the guidance system and range safety can track it correctly. Boosters separate after their burn is complete. That separation must be clean, with no recontact. The core stage continues to burn. Near main engine cutoff, the guidance system shapes the trajectory so the upper stage can finish orbital insertion. After core stage separation, the upper stage takes over. Orion remains attached at this point. The upper stage burn is smoother than the core and booster phase, but it still requires precision. It must place the vehicle into the correct orbit and with the correct timing for later burns. Once in orbit, Orion separates, and Orion begins its own checkouts. For a crewed mission, these checkouts are not only telemetry checks, they are also habitability checks. The crew verifies displays, switches, cabin pressure behavior, and the practical reality of living in the capsule. Then comes trans-lunar injection. For Artemis II, the upper stage performs the burn to send Orion toward the moon. After that burn, Orion separates from the upper stage. The upper stage is then disposed of, following a planned path to avoid creating long-term debris in useful orbits. From that point, Orion is a deep space spacecraft. It must manage its attitude for three main reasons: power generation, thermal control, and communication. These requirements can pull in different directions. Solar arrays need sunlight and a certain pointing. Radiators need a certain orientation to reject heat. Antennas need to point toward Earth for high-rate communication. Artemis II operations involve balancing these needs with a set of defined attitude profiles. Orion's propulsion system handles small adjustments called trajectory correction maneuvers. These are planned burns that correct small errors from launch and from earlier burns. The goal is to keep the spacecraft on a path that will meet its lunar flyby target and then return corridor. The burns are typically small, but they are important. A small error early can become a larger error later. Orion also carries navigation aids. Star trackers identify star fields to determine attitude. Inertial sensors measure rotation and acceleration. Optical navigation can use images of Earth and the Moon. These methods are combined. The ground team also provides tracking data through the Deep Space Network. The Deep Space Network is itself a critical asset. It is a global set of large antennas, primarily in California, Spain, and Australia, placed so that at least one site can see deep space targets at any time. But availability is not unlimited. The network supports many missions at once. Artemis II requires careful scheduling for data, voice, and potential video. There is also a human aspect to deep space comms, the rhythm of contact windows. When a spacecraft is in continuous contact, it is easy for teams to fall into a pattern of constant updates. In deep space, the team must plan what data and what messages matter most in each pass. Artemis II is a training mission for that discipline. As the spacecraft approaches the moon, the flyby geometry becomes more sensitive. The moon is moving, the Earth is rotating. The return corridor is a narrow region of space-time that leads to the correct entry conditions. Artemis II will use planned burns and tracking to keep within that corridor. During the flyby, the crew will likely capture images, but the main work is navigation confirmation and system monitoring. The moon's gravity bends the trajectory. The team confirms that the path is as expected. If corrections are needed, they are planned and executed with careful verification. After the flyby, Orion heads back toward Earth. The spacecraft remains in deep space for days. The crew continues to live in a tight capsule. Workloads are managed. The mission timeline includes rest periods. Even though the script does not focus on comfort, the reality is that fatigue and discomfort can create errors. Artemis II planning must account for this. The crew module and service module remain attached until just before entry. Near Earth, the spacecraft performs a sequence to separate the service module. The service module performs a final disposal maneuver or follows a trajectory that leads to burnup. The crew module then orients itself for entry. Entry begins at the top of the atmosphere. Heating rises rapidly. Plasma can form around the capsule, which can affect communications. The vehicle must maintain attitude. The guidance system controls the entry, using lift to manage deceleration and heating. After peak heating and deceleration, the capsule slows to speeds where parachutes can deploy. Orion's parachute system is large and complex. There are mortar-deployed parachutes, drogue chutes, and main chutes. Reefing stages control opening loads. The sequence is designed to prevent tearing or collapse. The final impact with water is still significant. The capsule must handle it structurally. The crew seats and harnesses must protect the astronauts. After splashdown, the capsule can roll. Orion has systems to right itself. Recovery teams then approach. Recovery is planned as a coordinated operation. Ships and helicopters are involved. Divers attach lines. The capsule is stabilized and brought close to the recovery ship. Then the hatch is opened and the crew is removed. Medical checks follow. The capsule is then secured for transport. Artemis II is also a mission that produces qualification by flight data for later missions. Even if every system meets its predicted values, NASA will still learn details. They will see how thermal models compare to reality. They will see how navigation filters perform. They will see how small vibrations affect sensors. These small deltas become design updates. A large part of Artemis II preparation is about building confidence in the integrated vehicle, but also about clearing specific known issues. One well-known issue from Artemis involved valves in the service module propulsion system. Cryogenic conditions and materials can interact in ways that cause sticking or slow response. NASA and its partners examined these issues and adjusted procedures and hardware. Artemis II benefits from that work, but it also carries the reality that deep space propulsion systems have many single-point sensitivities. Another ongoing focus is the heat shield manufacturing process. AV coat is applied and cured in a pattern of cells. Each cell must be inspected. Voids or defects must be controlled. Artemis. eye heat shield performance was a major success, but engineers still inspect how and where the material charred and ablated, because those patterns tell you if the thermal environment matched the model. There is also the question of avionics and software maturity. Orion uses modern processors and a complex flight software stack. Software is tested in simulations and hardware in the loop labs. But flight is the real integration test. Artemis II proves that timing, sensor fusion, and redundancy management behave correctly under actual loads. Now include a critical topic that often gets skipped in public summaries: abort modes after reaching orbit. If a serious problem appears after Orion is in orbit, but before translunar injection, NASA must decide whether to proceed, delay, or return. In low Earth orbit, returning is easier. The capsule can deorbit and land. But the timing of deorbit windows, landing zones, and recovery assets still matters. If a problem appears after translunar injection, the options narrow. A free return trajectory is attractive because it naturally returns to Earth. But a free return can still require small corrections to hit the right entry corridor. If Orion's propulsion is compromised, those corrections might be limited. Artemis II trajectory design aims to protect against this, but it remains a core reason that NASA chooses conservative paths. Also consider the launch abort system again, because crew safety begins at T-minus seconds. The abort system has to detect certain failure signatures, or be commanded by the crew or by automated logic. An abort can happen in the atmosphere or above it. Different abort regions have different parachute deployment timelines and landing zones. Some can lead to a water landing near the coast. Others can lead to a landing farther downrange. Artemis II planning includes coordination with the US Navy and Coast Guard for potential abort recovery. Now step to the role of the Canadian Space Agency in Artemis II. Canada is a key Artemis partner and is contributing hardware to the broader program, such as the Canadarm3 robotic arm for Gateway. For Artemis II, Canada also has a seat on the crew through a CSA astronaut. This reflects a long history of US-Canadian cooperation in spaceflight. International partnerships matter because Artemis is not an isolated program. ESA provides the service module. Japan and Canada contribute to Gateway. Many nations have signed Artemis Accords. This affects the political durability of the program. Artemis II is therefore not just a US event. It is a proof point for a network of commitments. Now address a practical question that often comes up. Why fly a lunar flyby instead of going straight to a landing mission? A landing mission is much more complex. It requires rendezvous with a lander. It requires docking. It requires surface suits and surface operations. It requires more mission phases and more hardware. Artemis II reduces the number of new variables. It focuses on getting the crew safely to lunar distance and back. This is the most direct way to build confidence without stacking too many untested elements. Artemis II also tests the human experience of leaving Earth orbit. That experience includes not only the view, but the sense of isolation, the dependence on a limited life support system, and the longer time to return if something goes wrong. NASA needs that experience to shape later mission rules. Now, add a layer of detail about the spacecraft interior, because crew operations is not a single item. Orion's crew module has seats arranged to protect astronauts during launch and entry. The cabin includes stowage for food and equipment. The crew uses restraints and footholds because everything floats. There are displays and hand controllers. There is also lighting that must support work and rest. Waste management is a known challenge in small capsules. Artemis II is short compared to a station mission, but it is long enough that waste systems must be reliable and usable. The mission is also long enough that small problems can become major distractions. Food is packaged for space. Water is rationed. The cabin atmosphere must remain within limits. Carbon dioxide scrubbers must maintain safe levels. These are basic but critical tasks. Now include the concept of mass properties and why they matter. In spacecraft design, mass is not only how heavy the vehicle is, it is also where that mass sits, which affects center of gravity and moments of inertia. These properties affect control and entry dynamics. For a capsule, the center of gravity is deliberately offset to generate lift during entry. If the mass is different than predicted, entry guidance must account for it. Artemis II vehicle mass properties are measured and verified to make sure models match reality. Now talk about the recovery zone and why it is chosen. Orion is planned to land in the ocean, often in the Pacific. The exact zone is chosen based on entry corridor, weather, recovery ship placement, and safety. NASA wants a landing zone that is reachable, that has manageable seas, and that reduces risk to the crew and recovery team. Artemis II will confirm whether predictions of landing dispersion match reality. Also, include the environmental and logistical footprint of the mission. Launching SLS requires large ground support, a large workforce, and significant consumables, like liquid oxygen, liquid hydrogen, and water for sound suppression. Recovery requires ships and aircraft. This is not a small operation. Artemis II is therefore a test not only of flight hardware, but of the ability to run a complex operation repeatedly. Now cover the immediate post-flight analysis, because Artemis II does not end at splashdown. NASA will collect data from the vehicle. They will look at engine performance, vibration signatures, thermal profiles, avionics logs, life support data, crew reports, communications quality, and many other channels. They will compare predictions to reality. They will identify discrepancies and decide whether they require design changes, procedure changes, or no change. They will also inspect returned hardware. The crew module returns. The heat shield is examined in detail. Parachutes are examined. The structure is checked for cracks or unexpected wear. Sensors and wiring harnesses are inspected. This inspection is part of building confidence for Artemis III. Now place Artemis II in the larger timeline of lunar exploration. Apollo missions were flown with a rapid cadence, but the program ended and much of the industrial base dispersed. Artemis is attempting to rebuild that capability in a more distributed, contractor-driven way. That means that Artemis II is not only a mission, it is a signal to suppliers, to NASA centers, and to the public that a crewed lunar program is real. The next steps after Artemis II depend on how it performs. If the mission meets objectives, NASA can proceed toward Artemis III with stronger evidence. If Artemis II reveals major issues, it can cause schedule shifts, redesigns, or changes in mission profiles. Finally, return to the simple summary of what Artemis II is doing, but now with context. A crew launches on the most powerful rocket NASA has built since Saturn V. They ride a capsule built for lunar return speeds. They travel beyond low Earth orbit, approach the moon, swing around it, and come home. Along the way, they test life support, navigation, communications, mission operations, and recovery. Artemis II is the bridge between a test flight without people and a mission that aims to land people again. This was a quiet archive story, where the story ends, sleep begins,